think we are ready to start. So I also like to thank Chirag for these great presentations. I'm also quite impressed and also take my own takeaway lessons. Now I know that I can ask a search engine or search system, what's the meaning of life? And I also learned that Facebook has ask questions option. So now I'll go home and ask that to Facebook. And if I find an answer, of course, I'll put it on my Facebook page as well. Coming back to my own slides, unfortunately, I don't have so much colorful slides and so much stories from Moscow as impressive as Chirag's and not funny anecdotes. So if you are going to blame me for having some sort of boring slides or technical slides, don't blame me, blame Alexandra, who pushed me, who pushed me, send your slides, we are going to put them on the page, you have to arrange this and this. So if you are going to blame someone, blame Alexandra. But from my point of view, I'd like to thank Alexandra and Pavel Serdyukov for arranging this meeting so that I can here talk with you guys. And also Yandex employee Pavel Braslavsky, who pointed me to the correct person, the correct people in this lab, so I didn't struggle a lot to find my way for coming to this room here at that time. So, coming back to technical stuff here, I'm from L3S Research Center. I don't have too much contact information here because you are people from Yandex, so you can just put my name on your search engine and can find enough information, I guess. But a couple of words about my research institute. L3S Research Center is located in Hanover, Germany. Our basic topic of research is web science. We have several subdivisions that are working on intelligent information access, middlewares, networking, security, future of internet, social aspects whatsoever. So whatever you can think of web science that we are trying to address in this lab, that's been headed by Professor Wolfgang Neidl for a long while. And coming back to the topic of my talk today, it is about efficiency issues for web search engines. So I will have a little bit technical stuff here, but I'll try to make it easy and probably not boring. But if you got bored, if you got depressed, or if you just don't understand that stupid formula, then just don't hesitate to interrupt. So here is a self-satisfaction slide that my previous research interests in the last decade. I will not go through the entire list, but the first two of them are the ones that I am currently working on. The first research issue is the efficiency and scalability issues for web IR. I think at least some people in Yandex will be interested on this topic. And the second issue is the social web. So we are now more interested in sentiment analysis or social ranking, and especially from a search point of view again, because that's what I'm working in. And coming to the particular issues I'm going to talk today, as I said, I'm working on efficiency and scalability issues for web IR. So we address two topics, caching and static index pruning. As I said, these are a little bit hard topics, but I will make them easy for you to grasp at that time of the day. So caching and index pruning are indeed sort of similar topics, similar issues in their nature, but the difference is that in the caching, if you have something in the cache, some data item, more or less you know that it is complete. So it appears as if it is in the original data source. When you do index pruning, as the name says, you are cutting off some parts of the index. So what you have is what is left from the pruning and may not be the same as the original data. That's the basic difference. But today we'll be focusing on caching. It is not an analysis or discussion of a single paper, but sort of a potpourri of a number of papers. So this idea, cost-aware result caching, is covered in two different articles recently. And again, the cache freshness idea for result caches is covered in CIR 2012 and ECR more recently. So this is some architectural view of a search engine. I'm hoping that more or less you are somewhat familiar with that. But if you are not, just a quick recap. On the left-hand side, according to me, you see the indexer machine. So the indexer machine has the inverted index for the data collection. For the web in its entirety. On the bottom you have the document servers, and again you have the actual documents and the servers that are keeping them. Of course, index servers and the document servers can be overlapping, so you can use the same machine for indexing and also keeping the documents, but here, for the sake of presentation, I prefer to distinguish them. And there is one broker for this cluster of machines. There's one or more broker machines, and these brokers are getting the query from the user. So when you send the query, it first goes to the broker machine for the cluster of these servers, and it goes to the indexers from the broker. And what indexers do is basically they go to the inverted index. Probably it is on their disk, so they fetch the posting list for the query terms, bring to their memory, and then make some intersection operation. As we all know, most search engines by default apply conjunctive semantics, which means that if you are writing a query like Moscow hotels, then you will have Moscow and hotels posting list, and you will make an intersection of them to find the documents that have both terms. So this intersection thing happens in the indexer machines. And then your results go back to the broker. Broker collects results from indexers, like top 10 results from each of the indexer machines, and then merges them, and probably applies a second level, more sophisticated ranking algorithm, like learning to rank or something. So now you have the actual top 10 results here created at the broker. And then you go to document servers, because at the broker now you know the document identifiers for your top 10 document, but you don't have the snippets yet. This result summaries, 1-line or 2-line summaries of the documents that appear in the query result page. So you go to the document servers and say that, okay, here are my top 10 document identifiers. Please give me the snippets. And document servers go to their own disk, gets the documents, and then in their memory they create the snippets, and then they just send them back to the broker, and broker puts them into a web page of top 10 results having the URL, title, snippet. And there is one crucial thing that I did not show here. Of course, the advertisement servers, that is crucial for the search engine. That's how you earn money. I didn't put it there, but of course, at the very end, you also get advertisement from your advertisement server, put it into the result page, and yes, you are done. You can send your result to the end user. So this is the basic architecture, I think, more or less you are all familiar with. So I mentioned 5 types of data items in this architecture. You probably saw them. So the first type of data item is the posting lists. You fetch it from the disk at the indexers. The second type of data item is the intersection of these posting lists for the query. So you compute it. It is not really, but you compute it in the indexer machines. The third thing is at the broker, you merge the top results from different indexers, and now you have the top K, top 10 document identifiers ready. It's again computed. The fourth data item you access is the documents themselves to create the snippets. And the fifth data item is the query result page, the final thing. So there are 5 types of things, and 2 of them are fetched, and 3 of them are computed. Basically, from computer science literature, we know that caching in operating systems, in proxies, in many other places, in instruction machines, whatever, are quite useful. So what you can do is for all 5 types of data items, you can cache them all. So here is the basic architecture again. Now you can have a list cache over there, so you don't need to go to the inverted index that's on the disk each time you want to reach a posting list. You can just cache them here. You can have the single posting list cache here for many of the terms, or you can even cache the intersections of these posting lists. So that is one recent work by Long and Sewell, and you can have, if Google.com is asked too frequently, you can intersect their posting lists and keep in the cache the intersection of the posting list. That's one place. The other place is, of course, document server. Now you can have the documents here in the cache, so you don't need to go to the disk and inverted disks again. And the most effective cache is the result cache. Why it is most effective? Because we know that, I think last year, Fabrizio Silvestri from CNR Italy gave a great talk here, and he also showed that the query logs has this power law property. It means that some queries are asked again and again, very popular, and some queries are very rare. So for these queries, which almost half of the volume, that are repeated again and again, if you have a result cache here, you are very lucky, because if you get the same query, Facebook, 1 million times per month, you don't need to go and compute the result again. You can just provide it from this result cache here. So in the result cache, you can have just the document identifiers of top 10 results, or better, just the final HTML page with snippets, titles, URLs, everything ready, just stored there. And when the same query is asked again, you provide this result to the end user. So it's very very effective technique. So this brings you efficiency because you answer query, you answer the end user's query very effectively, and also you reduce the burden on the back end. This huge cluster. And reducing the burden on the back end has meaning in finance because you don't need to run many millions of queries back there. You are not using electricity. You are not trying to cool the machines. You are effectively earning money. So how do you, in these three types of caches I showed you, what do you do for content selection? There are two basic strategies for content selection that's very well known in, again, computer science literature. One of them is considering the frequency of the previous items. So if they are more frequent in the past, probably they will be frequent in the future as well. So I can cache these frequent items in my caches. The second thing is recency. Again, if something is asked very recently, if you ask about, if 5,000 people ask about Michael Jackson today, probably they will also ask tomorrow. So I can cache the result of Michael Jackson query. So these are two basic techniques, and according to these two basic criteria, we have two different cache types. One of them is the static cache, so it is, as the name implies, it's static, it's mutable. So you put what you need to put into cache, and then you don't touch it. It stays there maybe for 1 week, and after this week, then you recreate the cache content in periodic maintenance. So it is aimed to capture long-term access patterns, like the Google query, Google.com query, Facebook query, Google Maps query, or Yandex query. So these are asked for many months or for many years. People still keep asking these, really. And there are dynamic queries, sorry, dynamic cache types. A dynamic cache is trying to capture the shorter-term access patterns, so bursty access patterns. It's like Michael Jackson dies, and the next day you got 1 million Michael Jackson queries. Or Euro 2012 comes, and the next day you get many millions of queries for this one. And finally, you have a hybrid cache, so you have a cache space, and you share some of them for the static cache and some of them for the dynamic cache. So, what's our contribution in this context? Our contribution is embedding the idea of the costs. Why? Because we considered several types of caches, but we didn't consider the cost of a miss. If you find what you are looking for in the cache, it's very good. It's a hit and you can use it. But if what you are looking for is not in the cache, then it's not always the same cost. Some items that you produce, that you compute, are easy to compute. They are very cheap. And some items might be very expensive. Assume one query that reads very long posting lists, millions of posting lists, like Google.com. Google appears in millions of documents, com appears in millions of documents, so you need to read really long posting lists and intersect them. And on the other hand, assume a very rare query, so you need to read only tens of 20 or 30 postings. So the query computation time is not the same. So if you miss the expensive query from your cache, then in practice, your system is producing more effort, losing more effort to regenerate the item that's not in the cache. So what we did, the basic idea, is embedding the idea of cost into the caching strategies that we discussed here, frequency-based or recency-based, and also into the evaluation of these strategies. So what is the cost? You have the cost of reading lists, so it is disk fetching cost. It's very expensive, by the way. You have the ranking cost, there's easy intersection cost plus sophisticated learning to rank cost. You have the cost of document access, again reading from the disk, and you have the cost of snippet generation, which is probably, again, a very tiny part of the cost. So what we did is twofold. For single-level caches, like result caches, we developed cost-aware techniques. And also for multi-level caches, we investigated how these costs are interdependent to each other. So this is the motivating scenario. Let's assume a single-level cache, just a result cache. So you keep the results of previously seen queries in this cache, top 10 results, let's say. And assume we are a very poor search engine, so our capacity is only one result page, so we can keep only one query's answer in our cache. Assume we only get 2 queries. I said we are a poor search engine. So queries A and B. the frequency, past frequency of the query A is 10. It's asked 10 times. And the past frequency of query B is 20. It's asked 20 times. So considering the basic frequency-based caching idea, you can see that, okay, we have to cache this query B because it's asked 20 times, so we will have a higher hit rate. We will find it more in our cache because it's going to be asked probably more in the future as well, and we will have a higher hit rate. That's true. Now let's assume the cost part. Let's assume that computing the result of the query A takes 100 milliseconds, and computing the result of B takes 10 milliseconds. Now the story is different. Now taking B in the cache doesn't make sense. Now you want to take the answer of query A into the cache because it provides you higher processing efficiency. It gives you less hit rate, and hit rate is just the counting of how many of the answers are in the cache. Yes, true, it gives you less hit rate, but when you look at the actual system performance, you will see higher processing efficiency because the costly thing that has been asked 10 times is in your cache. So the takeaway lesson here is take costs into account while caching and also while evaluating your system. What happens if you have more than one types of caches? Assume the same setup I described up to now here. So again, the same query A asked 10 times, query B asked 20 times, same costs. But assume that in addition to the result cache, you also have a list cache in the indexer. What happens? If you have a list cache and assuming that all of your terms appearing in the query A is cached in this list cache, now the cost of query A may drop from 100 milliseconds, can drop to 10 milliseconds. Because it is all posting lists are cached, so computing the answer of this query is easier, cheaper. You can do it in much shorter time. And now we came to a point that both queries, A and B, have the same amount of cost. And now it makes sense this time to cache result B, because they have the same cost, but now B is asked more, so it is better to take the one that has been asked more frequently in the past. The takeaway lesson here is that you have to take cost interdependencies between different data items into account while having multi-level of caches. And please note that in reality, probably here in Yandex, you will have more than one layers of caches. So you won't have only one result cache. You won't have only one list cache. Probably you will have all of these. So you have to take into account the interdependencies between the costs. Here we have this fancy graph from an IPM paper that will appear soon. I will not go over all the things, but it gives you that if you have results in your cache, then you have to consider the frequency of the documents. Or if you have list in your cache, then you have to reduce the cost of the result generation phase, etc. So we try to figure out how the costs of different items are related to each other. So I will only describe a couple of techniques for the single level result cache. Forget about the multi-level cache. It's a little bit too much tiring at that time of the day, but just assume the result cache, basic one, so you only keep the results of the queries in the cache. So you can, in the literature, you can solve this by a greedy solution to the knapsack problem. So for each query, you have the value of the query, and in the most strategies, the value of the query is its frequency in the past. So if the query Michael Jackson is asked 10,000 times in the past, and Obama is asked 1 million times in the past, then Obama is a more valuable query than Michael Jackson query. And you have to also consider the size of the query, because query result, because you put it in the cache. But for the query result, sizes are negligible. More or less, they are all the same, just a few kilobytes of data. So, and they are all equal for all query results, so you don't need to consider. As a result, for the most frequency strategy, what you do is you get the previous queries, you have the query log, you just look at them at the Yandex, and you sort them with the frequency, and according to the cache space you have, you just put the most frequent queries in your cache. That's it. That's the static cache, by the way. So what we do is, while sorting this, we first sort with respect to frequency, but there are many queries, especially in the tail of the query log or in the torso of the query log. There are many queries that have the same frequency. At the head, we said that the queries follow a power law distribution, so some queries are very, very popular. But the other queries in the torso and in the tail are less frequent. And you can find 1 million queries that all have the frequency 20. So how are we going to sort them? So at this point, we first sort with the frequency and then sort with the cost as a secondary key. This was one like a baseline approach. As a second approach, we consider the stability of the frequency. We just don't consider frequency as it, but we check that if the frequency is stable between the last weeks or last month, so there's not one peak and then it drops, but it is stable and at a high point. So we consider stability. And finally, we have this nice formula. While determining the value of the query to be cached, we take its cost, processing cost, to the time cost of generating this query result. We take its frequency and we multiply them. For the frequency, you see that there is an exponent k. Why we have this? Because we observed that if the query appears very, very rarely, say less than 20 times in a query log, then it is very likely that in the future it disappears. It never comes again. But if frequency is higher than this threshold, say 20, then it appears almost like the same frequency in the future. So we wanted to emphasize the queries that are more popular, and we wanted to de-emphasize the queries that are less popular. So this k value, the k exponent, is greater than 1. And we usually set 2 or 2.5 in our experiments. So these were the ones for static caching. And if we come to dynamic caching, then you know there are two baselines, least recently used or least frequently used. These are common from operating system courses probably. We defined a very weak baseline, least costly cached item. So if your cache is full, then you have to remove something from cache so that you can put a new item into the cache. And what you remove is the least costly item because it is cheapest to produce again. So we remove it and we put into the new item. We have the previous formula we have used for the static cache. We have a greedy dual size formulation that has been first formulated by Zhao and Irani. And we have an optimization of this. Again, it computes cost time frequency. But this time we again enrich it with this k. So that's why we have this k. So we again adjust the frequency value with this exponent k. So these are the basic dynamic strategies for caching. So you don't need to need a setup, but we just tried with millions of queries. That is being coming from an old query log. And this is the optimal thing if you had an oracle, if you could hire a magician who could say that which queries will be repeated in the future and which queries would not be repeated, then that's the best thing you can have. And by the way, y-axis is the query processing time. It's not hit rate anymore. We are not interested in the hit rate. We are interested in how much your cache really improves your system's query processing time. And when you look at this, the baseline is the best thing, of course. That's this oracle. And the red curve is the most frequently, just caching the most frequent queries from the past. And our cost-based strategies are these three. And you see we have a very nice improvement up to 3%. Recall that the improvement in this query processing time reflects to what you get, what you lose in the backend. So it means that gains up to 3% means that less processing in the backend, using less electricity, using less cooling, and wasting less money. Same results for the dynamic caching strategies. Again, this is the oracle. The top ones are the least recently used and least frequently used strategies from literature. Least costly use also does really bad. But this GDSF, greedy dual size algorithm with K correction, it's doing also very good. And this time we can get up to 6% gains in processing efficiency. So this was a quick, fast and furious sort of analysis of these cost-aware techniques. In the remaining 5 or 10 minutes, hopefully, I will a little bit discuss about an orthogonal direction that we presented in CGIAR 2011 last year, almost at the same time in August. So in this setup, we assume that we have a limited cache space, and we wanted to put into our cache the items that will provide us the best gain, best efficiency. Here, our motivation is totally different. We say that hardware is cheap. You can get as many memory as you want for your machines. Furthermore, if memory is not necessary, you can just get disk for the result cache, and you can put some of your cache into the disk. So storage size may not be an issue anymore. So you can have higher storage size and you can have higher hit rate. The plot on the left-hand side, borrowed from Jambazolo et al., shows that if you are increasing your cache size, then you are having higher hit rate. This black curve at the top is infinite cache size. You probably cache everything you see in the past, and you put them into your cache. There is no limitation in this space. And in this case, you have very high hit rate, up to 60%. But then the problem changed. It's not anymore the space problem, or it's not anymore what should we put into the cache. Now we have a different problem. We have an infinite cache. We can put everything we see into this cache. But the problem is that if I ask a query 2 months ago and you cache its result, and 2 months later, if I come back to your search engine and ask the same query again, would I be happy to get the same result from your cache after 2 months? So how fresh are your results? That's the problem. That's the age of the result, age of the hit in your cache. And again, the black curve is the infinite cache. And for an observation period of around 10 days, you see that the items in your cache are 5 days old. This means that if you are making Euro 2012 query, its result probably gonna change tomorrow because there are so many news, TVs, this, that coming from everywhere. But for the following 5 days, you are going to get the same result from this cache, which is not good. So the story or the point we want to research is we want to find a way which results in the cache are fresh, so you can give them back to the end user, and which results in your cache are not fresh, so you cannot use them as is, but you have to put a mark on them and you have to recompute these results. There's one nice solution. We also discussed this a little bit with, before this talk with the engineers from your company. That's time to leave strategy. It's very basic strategy. It's a decoupled approach. It means that you don't really know what happens in the underlying structure. You don't really know, and you don't want to know what is going on in the index, what has changed, what has updated, what new pages are added. You are blind to this. You just simply add a time to leave value. Each time you put a query and it is result in your cache, you also add a time to leave value. You say that, okay, this value, this query result would be valid for the next 6 hours. After 6 hours, you just mark this entry as expired. So if the same query is asked again, you have to go to the backend and you have to compute this result again. So it's very basic. So the answer would be valid only for some TTL time, time to leave time. That's a very easy thing to do. The worst thing is that you don't know if the answer was really expired or not. Maybe it was still fresh and you are doing redundant work. You are using your backend for some useless work because the answer was really still valid. Or maybe the answer became invalid after the first 3 hours. So then it is also bad because for the remaining 3 hours you are giving the stale answer from your cache. These guys also gave an interesting trick on top of this TTL idea, and they said that, okay, we have this query backend cluster there. Excuse me. We need some water supply. Yes. You have this backend. And these backend computers are running all the time, most of the time. So they are idle cycles. And what you can do is you can choose which of these queries have expired and send them to the backend while they are idle, while there is not the peak load there, but less than peak load. So your machines are still working, they are alive. So you just send these queries, and just like prefetching, you get their results before they are asked again. This is an easy trick, but very effective, by the way. And according to this paper, it's also applied in Yahoo's production system. What about the coupled solutions? In the coupled solutions, you are not blind anymore. You want to know what is really changing in the underlying index. What new pages are added, what pages are changed, what pages are deleted. And according to this information, you want to decide which queries are valid, which query results are still valid, and which query results are not anymore variable. And in this approach, they assume that the incremental index update strategy, it means that each time some new documents are crawled, you update your index, so your index is up to date almost all the time. So your index is in perfect stage. But you don't know which of your query results in the cache are not valid anymore. And they introduce a CIP module. So you are sending all queries in the cache to this module from one side, and you are sending all changes that you make to the index from the other side. And you match them using a spatial inverted index in there. And if you see that, okay, this document is deleted from the index, and maybe it is changing this query's result, so this query's result is not anymore valid. So let's put a cross here, and it's not going to be used from the cache anymore. So that's the very basic idea. This solution, by the way, gives very perfect results in terms of accuracy. So you have almost no stale results, no unfresh results from your cache. The downside is you put all queries to this module, you put all changes to the index to this module. So it's a little bit costly. You make lots of data transfer and you make this matching operation. So in terms of a distributed architecture of a search engine, I'll not go into details, but this is a little bit costly operation. So our contribution here, by the way, just 5 slides left almost, so relax. Our contribution here is, can we do better than TTL, this blind approach, and close to CIP in detecting stale results? So we want to be as good as them while catching the stale results. But in terms of the efficiency, we want to be better than CIP and as close as to the TTL. Because TTL is good in efficiency, but it is blind. CIP is good in accuracy, but it is expensive. So we want to be as good as TTL in terms of efficiency and as good as CIP in terms of stale result detection. So we will use a timestamp-based invalidation mechanism. So this is the architecture. This is one search node, but this is what we have in one indexer machine in the cluster. What do we have? We have an inverted index, we have terms, we have posting lists here, and there are some documents assigned to this machine. So each time the crawler gets new documents from the web, it sends them to the document parser, and all changes are at the same time simultaneously applied to this index. So this is a real-time updated index. What we keep here? We keep some document timestamp information. This keeps track of when does this document has updated, the last time this document has updated. And we also keep a timestamp information for the terms. Easy. So this also keeps track of when does this posting list last change, so when there is a last addition or deletion or something to this posting list. And in the cache side, we have the same information. We have the query, result, and timestamp of the query. And this gives you when does this result is generated. So it is generated 2 hours ago, 5 hours ago, whatever. And when there is a cache hit, when you send a query and it is found in the cache, we don't directly give it to the end user. We say that, hey, maybe this is a hit, but this can be a stale result. So we have to check this. We send it to our invalidation logic. And what our invalidation logic does is, it takes this timestamp value of the query. It takes the timestamp value of the terms appearing in the query, and it takes this usual top 10 results, the results of the query, their timestamps, these top 10 documents timestamps. So I have 10 timestamps for the documents, a few timestamps for the query terms, and the query's original timestamp, like 15 or 16 timestamps. I compare them, and I make a prediction that, okay, this query result might be really updated, and result can be stale. Or I say that, no, it looks like this result is quite valid. And if all search nodes say that the result is valid, then you decide that the entry in the cache is valid, and you send it to the end user. If one node says that, no, I suspect this result is stale, then you rerun the query. I will not go into the details of how we assign these document timestamps, but basically it is very easy. So if you add a document to your system, then the timestamp is now. If you delete it from your system, the timestamp is set to infinite. And if you are editing it, and if you are editing your document, modifying your document greater than a threshold, again the timestamp is now. For term timestamps, it is even more easier. So if you are adding posting lists, more and more posting lists, at a given threshold, so you say that, okay, I added almost, say, X% of the original length of the posting list. So it is enough new data, so I assign a new timestamp for this term. There's also a score-based one. I'll not go into this one. This is the result invalidation policy. So we say that we decide a query result is invalid under two conditions. The first condition, if there is at least one document appearing in the cached result, so that this document's timestamp is greater than the generation time of the query result. This means that this document is deleted or revised after the generation of the query result. So you have a query result, you have a web page that like yandex.ru, but you see that its timestamp is greater than the query's timestamp. So there is an update in this web page, so you cannot give this result as is before. So this is one possibility. The second condition is for all terms appearing in the query, you also check that the timestamp of the term is greater than the timestamp of the query. This gives you that there are some new documents in which these query terms are appearing. And furthermore, all of them are appearing. So it is very likely that there is one single document that includes all your query terms and that can get into your results. So this is a suspicious case. Let's also mark this as stale. So these two conditions are saying that. So these are the results. This black curve is, by the way, these are simulation results, of course, because we are not like you having a search engine of our own. So we just simulated using the Wikipedia data and edits and historical changes, etc. So this black line, black curve, shows the TTL. This x-axis shows that the amount of the redundant work we are doing, false positives. So that these queries were not stale, but we taught them as stale. So these are false positives. And we want to make this as low as possible, because if you have so many false positives, you are running your backend for nothing, for useless queries. And this y-axis is the ratio of the stale queries. So you are serving stale results to the end user, unfresh results to the end user. So we want both of them to be lower. So in the TTL case, it is very easy strategy, but you have very high false positive ratio and very high stale ratio. These three curves here are the CIP technique, and as you see, they are quite good. And our curves are these three, so they are in between. And what we are doing is we can do what we promise. So in terms of the accuracy, we are in between of these two. How about efficiency? In terms of data transfer, we just transfer these triples: query, result, and timestamp. In return, CIP is transferring all queries and all changes to the index to a module, so it's more expensive. And in terms of invalidation operation, as I said, we just compare timestamps, 10 or 15 of them, easy, just comparing integers. And here, you have to have an inverted index, an additional index on your queries so that you can do this matching. So as a result, with this work, we can keep our promise. We are very efficient, at least more efficient than CIP, and in terms of the efficiency. And in terms of accuracy, we are not as good as them, but we are close to them. And for TTL, just the vice versa appears. So we can have a compromise between these two extremes. Conclusion, finally. So what I can say as a takeaway message here is that data on the web is growing continuously. So we are having more data, more multimedia data, videos, audios, this and that, and social data, of course. So this has very big financial enforcements on the search engine architecture. So you have to more data centers, larger computer clusters, more networking bandwidth, and so on. And of course, more electricity bills, more cooling bills. So you have to make search efficiency as much as possible. You have to make your search as efficient as possible. Here I presented two strategies for the cost-aware techniques, for the caches with limited capacity, and for the caches with theoretically infinite capacity, we can use this invalidation approach. So we are keeping our work on efficiency track. So we are working on new strategies for better cache, for providing better cache freshness, and also for making our inverted indexes compactor. So if you are interested, just be tuned and check from time to time in our webpage. Last but not the least, I want to say thank you or spasibo. And if there are any questions, they're just welcome.